Hello, welcome to a digital logic design tutorial. Today we're going to see how to create a Quartus functional simulation. We'll use a block diagram schematic of logic gates and or not XOR and buffer, and then create the functional simulation. Okay. So let's get started by bringing up Quartus. So I started the Quartus software. Yours may look something like this. What we want to do is we want to create a brand new project. So I'm going to go to the new project wizard. So if you see new project wizard, you can click on that. If it doesn't show up there for you, you can always go to file, new project wizard. And it's going to go through a series of screens. So we'll click on next. There's not a whole lot we need to change. This first screen here is important. It's asking, what is the working directory for this project? Right, and it's trying to save it where my files are installed on this machine. And I just want to throw it out on the desktop. So I'm going to choose my desktop. And I'm going to create a folder for this. If you don't, it will, when we create a project, even a small project like this, it creates a lot of different files that will throw all over your desktop. So let's just say new folder. And I'm just going to call this lab 0. Here, and I'm going to make sure that is selected, select folder. What's the name of this project? I'm going to call that lab 0 as well. All right, when you name these projects, it's best to start them with the letter of the alphabet, upper or lower case. You can include numbers. If I have a long name, I usually use an underscore to separate words. Don't create a name with spaces. It often works with hyphens, but if you use any special characters other than an underscore, it will work with most operating systems, but once in a while it won't work and it won't create an obvious, easy to find error that you can fix. Things just won't work. So lab 0, click on next. Empty project is the default, click on next. We don't have any files to add, click on next. And it comes up and asks what board you want to use. We're not going to use any particular hardware. We won't program this to a development board. So we'll just use the default here. Click on next. We don't need to set anything in the simulation under the EDA tool settings. We're going to use the University Vector Waveform. So we'll click on next, and now we'll click on finish. Right. And that spinning wheel is setting up our project environment. All right. And so what we want to do now is we would need to create a schematic. So if we say file, new, and if we choose block diagram schematic file, say okay, right, that opens up a block diagram file. Now mine has the guidelines turned off here. I'm going to go to view and I'm going to click on show guidelines. You may be seeing something like this with guidelines. If you like those guidelines, that's fine. Right, it gives you an idea of where you put things on a schematic. I am going to turn them off for this. I tend not to use them for these tutorials. So I'm going to click on show guidelines so that it goes away. All right. I'm making the assumption that you know how these logic gates operate. If not, I'll include a link to another of my tutorials on the logic gates, what their truth tables are, how they operate. But for now, we're just going to insert those gates here in our schematic. In order to do that, one way to do that is you're going to right click with your mouse, say insert symbol. It's going to bring up this symbol window. By default, it's going to where the software was installed. You can click on this triangle to open up other submenus. Logic gates are under primitives. So if I click on that triangle, it opens this up. And if now I click on logic, it shows me all the different logic gates. Right? For instance, if I click on AND2, this is an AND gate. 2 indicates, so the number indicates the number of inputs. Remember, your logic gates, some of them may have multiple inputs. All of our logic gates just have a single output. Right. So I'll just go ahead and insert this on here for our AND gate. Right. And so you can see this better. I'm going to go up here and click on this magnifying glass on the zoom tool, make that active. So when I move the cursor back over here, you can see the magnifying glass. If I left click, this will, for each left click, this will keep magnifying things, and I can hit escape to get out of that mode. All right, so we've got our AND gate. We want to go ahead and add some other gates. So again, right click, insert symbol, and it brings up this symbol window where we last were. I'm just going to type not, N-O-T. That's the name of the not gate. Place that here. And again, insert symbol. The buffer gate is called a wire. So I'm going to type wire. Put that here. Right. And so besides the right clicking, there's also a tool. If you hover over this little icon that looks like a gate, you'll see it says symbol tool. You can click on that, and that will also open up this symbol window. And in this case, I want the OR 2. I want a 2 input OR gate. Here we go there. And when I use that mode, it has a repeat insert mode. So notice I left click to get this 2 input OR gate here, and it's got another OR gate here attached to the mouse cursor. If I wanted to put down another gate, I could just simply left click. To get out of that mode, I'll hit escape. All right, so finally now I'm going to right click, insert symbol, and I want exclusive OR, which is XOR, and there's our XOR gate. All right, there are gates. Now we need to attach inputs to this, and those come in the form of pins. So a couple different ways you can do that. Again, right click, insert symbol, brings up that symbol window. And if we scroll up, right, I'm going to close that logic. Notice here under primitives, there's a folder for pin. Click on that, and you can see they're bidirectional pins, input pins, and output pins. Let's go ahead and get our input. And I'm going to click on repeat insert mode. We're going to have 2 inputs. We'll name them A and B. So I left click, I hit escape. All right. And so let's connect pin 1. So let's make pin, so default names, as you can see, pin name 1, pin name 2. If I double click on this and get it to highlight all in blue here, I can just type over what's here and call this A with a capital A, hit the enter key, goes to the next pin. I'm going to call that B, except I hit the enter key before I type the B. All right. Another way you can do this, what just happened is if you highlight this, a lot of times by double clicking, I got it to come up and highlight everything. And now I've got the cursor, and I could just get rid of some things. I could type B. What I want to do is if I select the gate and right click, I can go to properties, and that brings up your pin names as well too. So if we hadn't already typed B here, we could type B, say okay, and make our changes. Right, when you name your pins, name them with letters of the alphabet, upper or lowercase. I'm using uppercase today to make it a little bit easier to see. You can use, as you'll see when we name the output pins, you can use multiple letters, numbers, and if you want to separate words, you use an underscore to do that. So the underscore is the only special character that you can use in the pin name. If you use spaces, hyphens, any other special characters, it will cause errors. All right, what I'd like to do is I want to connect A to the wire gate and the NOT gate. And so I am going to left click on this, and notice it's in blue, it's highlighted. I'm going to hold down my left mouse button, and I'm going to drag this. And I'm going to drag this all the way over here and just barely touch this. I let go, I drag it away, it's connected. Another way I can make this a wiring connection is I can move the mouse over here to the start of this NOT gate. Notice as I approach it, at some point it becomes a crosshair. Now, if I press the left mouse button down and start to move the mouse, it starts drawing a wire. And I'm going to draw this up until I get here. When I intersect the wire coming out of A, I'm going to let go. All right. Whatever you've just been working with is usually highlighted in blue. I just clicked again as I got away from there to unhighlight that. And you can see that this wire is connected here to this one. Whenever you see this junction dot, that means these are connected. So A is connected to the input of this wire buffer gate. It is also connected to the input of the NOT gate. Right. I'm going to go ahead and left click, grab B, drag B here, connect it to the input of the AND gate. pull this back a little bit. And now what I'm going to do, again, you can see I've moved the mouse cursor here. I've got the crosshairs. I'm going to left click, drag. I'm going to connect A to these other gate inputs. So notice here when I crossed over B's line, it didn't actually make a connection, which is good. We don't want it to connect to B. So you can just think of that wires laying over the top of the other one. All right. So now, right, A is connected to each one of these gates. B is connected to the AND gate. I also want to connect B to the OR gate. I'll do this, right? So the junction here from here to here, B is connected here. Notice it just went over the top of this other wire, didn't make the connection. So that round junction always tells you when the connection's been made. Right, so now we have A and B connected to all of our gates. Let's go ahead and insert output pins. Right, and so we could right click to do that. There's also a pin tool here. If you hover up here over these pins and you select from the drop down, you could select output. Every time I left click, it places a pin. I'm using the scroll wheel to scroll down, left click, and I'm going to hit escape to get out of that mode. Right. And I'm going to connect the output of this buffer gate here. Right. So I'm going to connect these gate outputs to these output pins, and then we'll name them. Same thing, I could grab one of these and do this to connect just as well. So whatever works best for you. All right, now to change these pin names. So I'm going to double click on this. Actually, I guess I'll right click, go to properties, and I don't want to call this pin name 1. I'm going to call this A naught to give a descriptive name to the output. Same way here, I'm going to right click on this, go to properties. I shouldn't have called that A naught, that's the buffer gate. These names have to be unique. So let me go back up here. I'm going to call this A buffer. Hit my enter key. Once I have this in this highlighted mode, if you hit your enter key, it will just go to the next one. I'm going to call this A underscore and underscore B, A and B. I'm going to call this A underscore or underscore B. Hit my enter key, A underscore XOR underscore B. Hit my enter key. All right, so the output of my XOR gate is going to be named A XOR B. Output of the OR gate, A or B, right? I'm separating the words with underscores. You could have written it, you could write it all as one. I'm just trying to do this to make it a little more readable. Trying to give these meaningful names. A lot of times when you first start creating circuits, we have truth tables and we say, well, the output of our circuit in our truth table is named F. Well, if we have multiple outputs on here, they all have to have unique names. So we couldn't have 5 outputs named F. We could say F, G, H, I, J, K, but that's not quite as meaningful to let us know what those outputs are connected to. That's why I tried to use the name of the gate here in the output names. All right, now we've got all of these connected. Let's go ahead and save this. By default, when it creates this, it creates the file with the name of block1.bdf. You may not be able to see this. You should, well, my students will be following along. If you're following along and creating this as well with Quartus, you'll see, whenever you see an asterisk after a file name, that's Quartus's way of telling you that file hasn't been saved. So let's go to File, Save. By default, it's going to use, we use for the name of our project, we use Lab 0, which that's what it also used for something called the top level name. Just go ahead and keep that same name for this example. In another tutorial, I'll show you how to create top levels with different names. For now, let's just do this. All right, click on Save. All right. If you go over here and under Hierarchy, go to Files, you can see this file is now part of your project. When we said File Save, there was a box there that was checked by default that says add this file to the current project environment. All right, I'm going to go back to Hierarchy here. All right, what we need to do before we can run the simulation is we need to run analysis and synthesis. Right, so I'm just going to go down here. I'm going to double click on this. This won't be a very long process. what it's doing, it's checking my wiring, it's checking the syntax of what I've named the pins. While it's doing that, one thing I want to mention, notice then when we got these gates from the Quartus logic primitives library, every gate has the name. So the name not lets you know that's the not gate besides the symbol. And everything has a unique instance number, which Quartus then calls, always starts with the name of INST. So the first one we put down was the AND gate. So the first one you put on a design usually is just called INST. After that, it starts appending numbers. We added the NOT gate, so INST1, INST2, INST3, INST4. All right, so everything has to have a unique instance number. Quartus did take care of that for us. Now, so everything went ahead and programmed correctly or survived analysis and synthesis. So analysis, that's what's looking at your schematic to see if everything's wired correctly, named correctly. Synthesis means it's going to try and synthesize this to hardware. Now, we're using symbols that represent the hardware, so it's going to synthesize its representation, the symbol, to an actual AND gate behavior, right? Which only makes sense. Right. Synthesis is more commonly, we'll talk about it when we start talking about Verilog and how it synthesizes Verilog to particular forms of hardware. All right, if you get errors, they show up in red as these messages come out. You can always click over here on this red icon for show error messages. If we do that, notice there's none, that's a good thing. There's warnings, right? So click on the warning symbol. So by default, you get this warning number of processors has not been specified. That's not going to hurt anything. I will show you how to correct that in another tutorial if you want to get rid of that warning. But that one's okay to leave in for right now. After we successfully run analysis and synthesis, we can actually then create our functional simulation. To do that, we're going to go to File, New, and let me minimize this. Yeah. So I was going to minimize this in the background, but what you want to do is you want to scroll down and you're looking under verification debugging files, university program VWF, so vector waveform. Click on OK, and that's going to open up another window. I'm just going to maximize this here. Here's your simulation window. And so the first thing you do is go to File. Go to Edit, set end time. For us, we want our simulation to run for about 20 nanoseconds. So I'm going to backspace here. I'm going to type 20. I'm going to hit the tab key to go, well, actually hit the tab key, or you can go over here and select from the drop down. US is microseconds. We want to select NS, nanoseconds. We click on OK. And so now we've got, we're going to run a simulation for 20 nanoseconds. We also need to add our pins to this from our design. We can't do that until we've actually successfully run analysis and synthesis. But now if over here on the left, if we go ahead and we right click and we say insert node or bus, we go to node finder, we go to list. So by default, pins all, we list, that's going to list all the pins in our design. So those are the nodes that it found. We want to select, you can just, we want all of the nodes. So to get all of the nodes, double click on what looks like the double greater than sign to bring them over here. Click on OK, click on OK. And notice now all of our pins show up over here in our design. And so you can see then the input pins show as in, output pins show as out. I'm just going to, you can move things around. What I'm going to do is I'm going to save the simulation. I found that sometimes Quartus will crash if I start moving things without having saved them. So File, Save. By default, this is going to save this in this project file we created. So this Lab 0 folder, it's going to save it. It's going to give it a default name of waveform. We're just going to go with that for this tutorial. And in another tutorial, I will show you how to give it different names. It's going to save it with the extension of .vwf. And notice that this box is checked for add file to current project. We do want it in the current project environment. All you need to do is click on save. All right. Now what I'm going to do now is I'm going to left click, highlight B, and I'm going to drag B up here. And so now we've got all of our inputs and outputs together. And what I'm going to do is I'm going to control click on A so that I have both A and B selected. I'm going to right click. I'm going to choose grouping, group, and I'm just going to name this input. And notice now all we see is input. We can't see A and B, but notice there's this little triangle to the left. If you click on that, you've got values for A and B. By default, A and B are both zeros. So this line that's low, that's all the way across, is a 0. Right? If I just highlight A, and if I go up here and click on 1, forcing high, that would force A high for the entire simulation. Notice this input grouping I find to be handy because it shows us all of our binary combinations of our values. All right, so I'm just going to go with A still highlighted. I'm going to go back and make it 0 again. So when the line is low, it's 0. When it's high, it's a 1. Our inputs in our simulation are what we're going to set. When we actually run the simulation, then our outputs will be populated. So here, when you're setting up your simulation, your outputs will have these crosshatches because their values are not known until we actually set the input values and run the functional simulation. Right. So part of the reason I also made an input group as well is I'm going to highlight this input group. I'm going to go here. So I'm going to hover over what looks like a C. When you hover over, it says count value. I'm going to left click on that. And it comes up with a starting value of 0, 0. I want it to increment by 1. I want it to give me a binary count. And I'm going to use the default of count every 10 nanoseconds. So if I click on OK, what that does is you can see for the first 10 nanoseconds, it started with a count of A is 0 and B is 0. So this binary input 0, 0. And then in the next, after 10 nanoseconds, it's at B high, left A low. So it counted from 0, 0 to 0, 1. That's using a 10 nanoseconds. Let's, again, I'm going to go up here. So with input highlighted, I'm going to go back to count. And let's just tell it to count every 5 nanoseconds. So every 5 nanoseconds, now it changes the count. It started at 0 as we told it. It incremented by 1. So we get 0, 0, 0, 1, 1, 0, 1, 1. And that gives us all 4 possible inputs. Those gates that have, right, the AND gates that have 2 inputs, we want to test them for every possible binary combination. So we'll test it for 0, 0, 0, 1, 1, 0, and 1, 1. Right. Now we need to save that again. So file save. Now if we go to simulation, run functional simulation, it's going to throw up a window, run a bunch of commands. Green is always good. It's going to run that, and it's going to produce showing on my other screen. So I'm going to pop this up. Here is your simulation output. Now let's take a look at A naught. We know that whenever A is a 0, the output of the NOT gate should be inverted, should be a 1. So I'm going to control click on A. Let's take a look at A. And so you can see here from this time from 0 picoseconds all the way up to 10 nanoseconds, A remained low. Our output A naught is high from 0 to 10 nanoseconds. At 10 nanoseconds, when A transitions from 0 to 1, so when A becomes a 1, the output of A naught becomes a 0. Right? Functional simulation of the gate for the NOT gate is correct, as we would expect it to be from the Quartus library. Right? If we take a look at the buffer gate, so we have the A input connected to our buffer gate. Remind you of what our schematic looks like. A input connected to this wire gate. Let me pop that simulation output back up. That's what the one we named A buffer. Well, a buffer gate, the way it works is whatever the input is, the output is the same. So if the input's a 0, the output's a 0. So again, I'm going to control click on A. You can see as long as A is a 0, the output of A buffer is a 0. When A transitions to 1 at 10 nanoseconds for the remainder of the simulation, the buffer gate output is a 1. Now let's take a look at our AND gate. So A and B. Right. We know the way an AND gate works is the only way you get an output of 1 is both of the inputs have to be 1, 1. But let's look at the case here during this time period here. All right. So this time period here, when A and B are both 1, 1, and if you just want to get this, A and B are both 1, 1, our output, and if you want to see the net name a little bit better, I can move that. A and B are outputs of 1. For every other binary combination, A AND with B is a 0, because if any of the inputs to an AND gate is a 0, we'd expect the AND gate output to be a 0. Right? The OR gate is the dual of the AND gate. So let's look at A or B. We know the only time the OR gate generates an output of 0 is when both of the inputs are 0. So let me go here. No, I don't know where. There we go. Just trying to get this to come across. All right, so from here to here, from 0 to 5 nanoseconds, the output of the OR gate is a 0. Both of our inputs are zeros. For the remainder of the simulation, the output of the OR gate is a 1, because at least one of the inputs is a 1. And of course, where both of the inputs is a 1, the output is a 1. All right, so when you run a functional simulation, what you do, of course, then is check to make sure that the output matches your truth table. Right. Finally, if we look at the XOR gate, the exclusive OR gate here, the exclusive OR gate generates a 1 whenever the inputs are different. So when we have two inputs, A and B, when they're the same, the XOR gate, the exclusive OR gate output is a 0. So you can see here in this first time period from 0 to 5 nanoseconds where A and B are both zeros, exclusive OR generates a 0. But from 5 nanoseconds, right, to 10 nanoseconds, A is a 0, but B is a 1. So the output of the exclusive OR is a 1. And then here from 10 nanoseconds to 15 nanoseconds, well, A is a 1, B is a 0, exclusive OR output is a 1. Finally, at 15 nanoseconds, when both of the inputs are 1s, the exclusive OR gate output is a 0. So all of these gates are behaving correctly. Like I said, these are part of the Quartus library. We would expect them to. The purpose of this was simply to show how the mechanics of running a functional simulation with some of the most basic circuits that we have. Now, if you needed to capture something like this for a lab report, you might need to take a screenshot. The one thing I don't really like about this output, and that's probably a function of this maybe being the Prime Lite software, which is free, and I appreciate that from Intel, is you can't save this. It would be nice to be able to save this, right? But your output window, you cannot save. So if you need something like this as a screenshot for a lab report, sometime you want to grab your screenshot while you have it open. It's a read-only. As you can see, the file is read-only as well, so that we can't make any changes to it. I'm going to close the output file. All right, we still have our input wave file. I'm going to close that. I'm going to pop this back up here. If I change then under Project Navigator from hierarchy to files, you can see that this waveform is now part of our project. And you could always open this up again. Right? If for some reason you had to make a change to your circuit here, right, what you would do is, so what happens a lot of times is when people are new to Quartus and drawing things schematically, they tend to overdraw their wires. So I'm going, by that, I'm going to go up here, click on the wire tool. So the other thing you can do is single wires. You can click on the wire tool. I've got this in wire mode. I'm left click holding down, and sometimes people will draw a little too far into here. And I'm going to hit escape. And sometimes, see how there's a junction box here, but see the important thing is this X in here. Sometimes when you actually draw too far into here, Quartus will act like you shorted out the circuit. So when you do that, you want to get rid of that. So let's say we did that before. To get rid of it, I can just actually click on a highlight, hit the delete key, it goes away. And once I make a change to the circuit, I need to save it. So I can say file save, or Control S does the same for me. And anytime I make a change, if I want to run that simulation again, I need to run analysis and synthesis again first. So I'll double click analysis and synthesis. Right. Or if we made some other changes to our logic, we'd have to do that. But that would be our only probably change at this time. So analysis and synthesis runs fairly quickly. And so now if you made that correction and need to rerun your waveform, all you need to do is double click on this to open the file, go to simulation, run functional simulation. It's going to run that and generate your output again. All right, that's all for this tutorial. That shows you how to do a basic functional simulation. I'll be making a new series of videos on how to create simulations with other circuits and how to create other circuits. But thank you for watching. Hope you come back in the future to watch more. If you found value in this, I'd really appreciate you clicking the like button there on YouTube. Thanks a lot. See you in the next video.